In this video, I'm going to continue looking at solving the radial equation for the wave function of a hydrogen atom. And so in the previous video, what we did is we did a bunch of substitutions, which I have written right here. And using those substitutions, we got our Schrodinger equation into this differential equation form, and that's pretty much what what the point of the previous video was making all these different substitutions in order to get our differential equation into a form that we want here. And remember, this is just looking at the radial part of the equation. We can still use the spherical harmonics that we got in our infinite spherical potential. And so right now we're just solving for the radial part of the equation, and we'll see at the end probably of the next video that we can then put this together with the spherical harmonics to get the full solution to the Schrodinger equation for a hydrogen atom. And so in this video I got a little bit lazy and I just kind of copied or took pictures of everything from the book because I didn't feel like writing all this down, which would probably be kind of boring for you. And anyway, a lot of this stuff is stuff that I've talked about in previous videos, especially in my differential equations videos. So once again, if you haven't watched those, watching those would be a really great idea if you want to really understand what's going on here. And so to kind of get into it, this starts right after we got this differential equation here, and it says that we assume that a solution, so these v's here, which are a function of rho, and that's how we get this v as a function of rho right here, that we can solve these as a power series. And so it'll be something that looks like this. And so we have a second order derivative here and a first order derivative here. So we have to take derivatives of these power series. And so the first derivative looks like this. And then the second derivative will look like this. And then we want to plug those back into our equation. So at this point here and at this point here. So when we plug those back into the equation, we get all of this right here. And you can probably see why I didn't feel like writing this all down. And so we can see that right here we have that second order. We have that second order right here, and then we have the first order right here, the first order derivatives. And so we end up with that, and then we can sort of equate the coefficients with like powers. And once again, I kind of went over this in my differential equations playlist if you were interested in seeing what that actually means. But then we end up with this right here, and then we can sort of move some things around to get what we have right here, which is the recursion formula. And so that's just how we determine each of the coefficients in what will be our solutions to the Schrodinger equation. And kind of a spoiler, that will be the associated Laguerre polynomials. And I will probably get to that in the next video. So we end up with this as our recursion formula. And then in the book, they want to look at what we have for large J. And so we end up with this. So it's essentially saying that these J's here are dominating, so we can sort of ignore all this L and everything. So we end up with this, then we cancel out these two J's, and we end up with this. And so we end up with this recursion formula. But what this is saying is that if we assume that this is the exact result, we end up with this here, which blows up at large rho, which is what we didn't want. We don't want this to blow up. And so what we have to assume is that the series terminates, that our power series terminates and becomes a polynomial, with a polynomial just being a power series that doesn't continue on to infinity. And like I said, that's how we're going to end up with the Laguerre polynomials. But anyway, so we want to assume that there is some number, this uppercase n here, such that if we put that in for our j here, that there is a number one lower here that will not equal 0, that we will actually get some, that we will actually end up with some coefficient. But then anything higher than that, we end up with 0 as our coefficient. And so you can imagine, if we have a power series, we have something that's like C naught x plus, well, I guess that actually wouldn't have the x. So we have C naught plus C1x plus C2x squared plus C3x cubed. And we're saying that after this 3 here, say our big N is equal to 4, then C3 is n minus 1, so big N minus 1 is equal to 3. But then we're saying that this is 0x4 plus 0x5 and so on. So this all gets crossed off and we terminate here at this big N minus 1. But then what we end up with is this, because if we have our j here be our big N there, then we end up with this 2 times big N plus L, and we have our big N, which is this j here plus this 1 here. So we're combining those two into our big N, and then we have the plus L here. So it ends up being that 2 times big N plus L, then minus this rho sub naught. That's what we end up with here. And we're saying that this has to equal 0, because what we want is for this whole formula right here to become 0. We want the numerator to become 0 when we get to that big N. And so that's what this is saying right here. And then we are just defining this big N, this uppercase N plus L, as being this lowercase n, which if you kind of know where we're going, that you know that that is our principal quantum number. And we'll talk a bit more about how that works probably in the next video. And so we have our P sub naught equals this 2 lowercase n, because we have this 2 here, and then we defined this as our lowercase n, then we just added rho sub naught to both sides, and so we have our rho sub naught equaling 2n. And it says rho naught is what determines our energy here. And so we end up with our energy equaling this h bar squared times kappa squared over 2m. And that comes from this up here. So it's just rearranging, it's just squaring everything to get rid of that radical, and then just sort of multiplying both sides by the h bar squared that results from that, and then dividing both sides by the minus 2m. And I have that sub e here because it's the mass of an electron. And so that's how we end up with this right here. And then we get all of this right here, so we can have that equal to that right there, because now we are substituting from that kappa there, which comes from this right here. So it's essentially just multiply both sides by kappa, divide both sides by rho naught, and then using that kappa, just using that kappa, which would be equal to sort of all this stuff, but then, you know, that kappa right there is now the rho naught, and that's where all of that comes from. And so this gives us the allowed energies because we have, remember, we have our rho sub naught equal to n here. We have our rho sub naught squared here. And so we end up with this n squared right here, with that 2 kind of getting shoved over right there, because we want to get this in a form that looks like this. And so that is our energy over the n square, where n can be equal to the 1, 2, 3, so on and so forth. And this is the Bohr formula, which Griffiths notes that by any measure, the most important result in quantum mechanics, Bohr obtained it in 1913 by a serendipitous mixture of inapplicable classical physics and premature quantum theory. So essentially, he's saying that, you know, Bohr got this by making assumptions that, you know, he didn't really have any right yet, and in 1913 to assume, and that assumption being essentially that energy is quantized, which wasn't really well established yet at that point. And so combining equations 4.55 and 4.68. So 4.68 being this, 4.55 being I believe this one was equation 4.55, and so we end up with this equation here. Then we just sort of define all of this as being 1 over a, where a is actually this Bohr radius, and so that's a radius that you end up finding a lot in quantum mechanics. And whenever I end up getting around to things like inorganic chemistry, we will probably see that pop up again. And so we end up with that, and so our kappa is now this 1 over an, and so then we have our Bohr radius. It follows from equation 4.55, so remember we had that equation where rho was equal to our kappa r, and then this is saying that kappa is equal to 1 over an, and so combining these two together we get rho equals r, or I guess we could say that it is 1 over an times r, which is just r over an, and so that's how we get that. Then we have the spatial wave function is labeled by 3 quantum numbers. That's our principal quantum number, our angular momentum quantum number, and I think the m is the magnetic quantum number, but it still has to deal with the angular momentum. And so this is going to be our equation right here, our solution of the Schrodinger equation, where the r is the radial equation and this y is our spherical harmonics. And so this is our radial equation solution here that we have obtained, and it says that v rho is a polynomial of degree n minus l minus 1 in rho, whose coefficients are determined up to an overall normalization factor by the recursion formula. And this is our recursion formula here, and that comes from this equation right here and this equation right here, which we already solved. This was our recursion formula, and remember we had our rho sub naught being equal to 2n, and so we can actually sort of just put this rho, because it's equal to 2n, into the parentheses here, and that's how we end up with our n right here. And that is where I'm going to end this video. In the next video, I'll start talking about looking at the actual solutions and sort of the actual particular solutions by sort of finding these different coefficients. And we'll see that this recursion formula is the recursion formula, as I said, for the associated Laguerre polynomials. And then we'll sort of look at the actual solutions of the Schrodinger equation, bringing together this radial equation with our spherical harmonics and sort of bring this all together. But anyway, so this video, like I said, we kind of went from where we ended our last video, getting our differential equation in this form, and we did that by using these substitutions, and then assuming that we could use a power series as solutions. We then found that that blew up to infinity, so we said that our power series had to terminate in a polynomial. And then we found that the polynomial, so we wanted to find these c's here, which we got from our recursion formula, which was this one right here. So these different c's come from the recursion formula there. And then we said, because this terminated, that we got this recursion formula right here. And anyway, that is kind of what we ended up getting from our differential equation. And like I said, we will continue looking at this in the next video. I hope you found this useful, and I will see you in the next video.